Hello all, welcome back to this online recording sessions in deep learning, okay, in the series of data science concepts. Okay, so in this session we are going to see what is vanishing gradient problem. So how to overcome this vanishing gradient problem with the help of various activation functions that can be used. Okay, so let us see first the vanishing gradient problem. So what exactly it is. Okay, yeah, so let us see the first the definition of vanishing gradient, then later on we can contrast in respect to the deep learning. Okay, yeah, so during back propagation, okay, so during back propagation we keep on updating the weights, we keep on modifying the weights until the predicted will be matching to the actual value. Okay, so we'll be modifying the weights. Okay, so if we keep on modifying the weights, what happens with the help of activation functions? If you see the activation functions, they are suddenly exponentially rising. Okay, so if you see sigmoid functions, sigmoid function, tanh functions, they are exponentially rising. Okay, they will with full speed they will fire like anything. Okay, so with more energy. Okay, so that means if this is the case, then we'll have many difficulties, okay, with the help of activation functions. Okay, sometimes the neurons will be also disappearing. Okay, they may go to far away infinity, they may disappear. That is what we are calling it as vanishing. Okay, they will vanish, they will fire to exponentially to infinity. Okay, they will be not visible to the our considerable our architecture. Okay, so our architecture may be constrained to some different parameters where it can be visualized, where we can work on with the available parameters, right? So if the neuron is fired with more energy to infinity, then that neuron may not be visible for consideration and to be worked on, okay, with all the concepts that are related in deep learning. Okay, yeah, so that is what the vanishing gradient means. The neuron will be vanishing during back propagation. Okay, so sometimes they also become very smaller. Okay, sometimes they may very become smaller for negative values. We have seen the activation for negative values, positive values also. Okay, so for negative values it may be minus infinity, minus some very large value. Okay, so in that case also the neuron may be diminished. Okay, if the neuron is infinity, if the neuron is too small or very small, the value is very negative. In that case also the neuron fails to give output to the remaining neurons. So this scenario is called as vanishing gradient. Okay, this scenario, the entire scenario, we are calling it as vanishing gradient. Okay, yeah. Let us see in contrast to deep learning. So what exactly the deep learning in contrast? Okay, so vanishing gradient problem refers to the diminishing gradient during the training of deep neural network. Okay, so as I said, with the different activation functions, the neurons start to disappear by getting fired to infinity or very less values or zero values. Okay, so in that case, in contrast to deep learning, the neurons get depleted. Okay, they may not be coming to the actual architecture where we are trying to create a model. Okay, so it occurs when gradients propagate backwards through the layers, become very small. Okay, so they do not help in supporting the weight updation. Okay, so next, why does the vanishing gradient problem occur? Okay, so again due to various activation functions. Okay, so vanishing gradient problem occurs due to chain rule. Okay, what is chain rule? Memmetization we have seen in back propagation, right? So we will be modifying the weights. Okay, so we'll be applying derivatives, okay, to the weights. Okay, so during this due to this chain rule, there will be a vanishing gradient problem. Okay, and the choice of activation function also. Okay, so the one case is because of chain rule, the other case is due to activation function. Okay, these are the two main reasons for the cause of the vanishing gradient problem. Okay, that is nothing but disappearing of the neurons from our architecture model. Okay, so when gradients are repeatedly multiplied during back propagation, they can exponentially decrease or vanish as they propagate through the layers. Okay, So activation functions like sigmoid function are prone to this problem because their gradients can approach to 0 for small inputs. Okay, for small or for very large inputs, activation functions like sigmoid, they may approach to 0. Yeah. So how to overcome it? So what is the solution? What is the solution that we can bring out in order to not to get the neuron to dead? Okay, in order to not to make the neuron dead, okay, we can come up with a solution. Okay, we can use various functions like ReLU, leaky ReLU, etc. to overcome this vanishing gradient problem. Okay, so let us see these concepts. Okay, what are the different vanishing gradients, what are the different ReLU activation functions that we have, and how they help us in overcoming the vanishing gradient problem. Okay, so this is ReLU activation function. Okay, yeah, we have seen during activation functions concepts also we have discussed. Okay, so ReLU activation functions will execute the neuron step by step, not at once. Okay, and also it will stops the dead neurons or weak neurons. Okay, it will not allow the weak neurons, it filters. Okay, ReLU activation function. Yeah, so this is the link that you can go through in order to study more about ReLU activation function. Okay, in simpler terms, ReLU allows positive values to pass through unchanged. Okay, while setting the negative values to 0. Okay, it will stop the negative values or weak neurons. Okay, yeah, in order to overcome the vanishing gradient problem. Yeah, this is the actual ReLU activation function, and the mathematical equation also you can see it here. For negative values it is 0, for positive values it is f of x is equal to x. Okay, so if the f of x is 2.5, x's value is also 2.5. Okay, so it is directly f of x is equal to x. Okay, you can see it here. This is ReLU. Yeah, what if I modify? Okay, what if I modify and consider how the leaky ReLU looks? Okay, so the leaky ReLU introduces small slope. Okay, you can see the slight difference, slight slope like this, dotted lines with dotted lines. See, right? Okay, what is this? This is alpha. This alpha value is 0.01. Okay, so f of x is directly proportional to x, right? In ReLU, f of x is equal to x, but in case of leaky ReLU, we have a constant. F of x is equal to, here constant is 1. Okay, that's why f of x is equal to x. Since so I'll write here f of x is directly proportional to x, right? Okay, so if I remove constant, f of x is equal to a of x, right? So here a will be 1 in case of ReLU. That's why we are not considering a value, we are just telling f of x is equal to x. Okay, so but here we have some parameter. Okay, alpha value will be equal to 0.01. Okay, okay, then if you plot it, will look like this. Okay, so you can see here in the legend also, the orange color represents leaky ReLU, the blue color represent the ReLU. Okay, they are just overlapping. Then you can see spot the difference here. There is a slight variation, that is nothing but a 0.01. Okay, okay, the slope for the negative values instead of putting 0. Okay, so the negative values also here they are considered. Instead of directly making or not allowing the negative values or the neurons which are having 0, instead of directly avoiding them, we are setting up some parametric value that is nothing but 0.01. Okay, so with this parametric value, the negative values will be also considered here. Okay, next, parametric ReLU. Okay, so here parametric ReLU means it is similar to leaky ReLU, but here the alpha value is varies. It is not fixed to 0.01, but it is varies. Okay, so parametric ReLU is an extension of leaky ReLU, where slope of negative part is learned from the training. So during training it will learn. Okay, so it will not be constant, instead it will be learning during the training. So that is what the parametric ReLU is about. Okay, and that is what you can see here. So in parametric ReLU, alpha can be adapted to different training conditions, so making it more flexible compared to leaky ReLU. Okay, so as during training, this leaky ReLU is getting modified according to the training conditions. Okay, so that means we have an advantage than ReLU and leaky ReLU, right? Yes. So it is advantageous than leaky ReLU and ReLU, because it is very flexible, and we can the negative part is also be considered. So instead of see, if I lose neuron, no, indirectly I am losing the information from the neuron. Neurons will be carrying information, right? So if the neurons are dead, or if you are trying to omit it, means nothing but we are trying to delete the information. Okay, so that's what. So it is parametrically tuned. So that's why we are calling it as parametric ReLU, and the graph is like this. Okay, it varies. Okay, it may be also like this sometimes. It depends upon the alpha value. Okay. Next, exponential linear unit. We call it as ALU. In ALU, you see there is a curve here. Okay. So exponential linear unit adds smooths by introducing non-zero slope. Okay. So here for it will be 0, right? If the points are here. But here we are adding a slope with the help of exponential function, by adding exponential function. Okay. So alpha exponential of e power x minus 1. Okay. So you can see the equation here. Okay. So the formula is here. Okay. Which reduces the bias shift known as the faster convergence in some models. Okay. So we can reduce the faster convergence. Okay. If the neurons are coming very fast. Okay. This is what the mathematical equation and graphs looks. Okay. We are having here slope here. Okay. That's the main difference. Okay. Yeah. When to use ReLU? Okay. Okay. In what cases the ReLU actually supports? In order to support handling sparse data. Okay. What is sparse data means? Zero data. Okay. Nearly zeros data. Okay. So if the data are nearly 0.001, 0.00001. Okay. This is what the values which are nearly to 0, we call it as sparse data. Okay. So if you are, when we are handling sparse data, we can go with ReLU. Okay. By zeroing out negative values. Okay. Negative values can be also zeroed. Okay. So faster convergence. Okay. So ReLU helps us in faster convergence. So ReLU accelerates training by preventing saturation. Okay. So there will be no saturations. Okay. Okay. So then indirectly there is a faster convergence. Okay. Yeah. So that is what, when to use the ReLU. So on the whole, we can say that ReLU is overcoming the problem of vanishing gradient problem. Okay. So there is a problem of dying of ReLU. So people also say in some cases the ReLU activation functions will also die. Okay. Why? In what cases? Okay. In neural network, why? How it happens? Okay. It refers to neural becoming inactive. Okay. So that means when the ReLU activation function dies, it becomes inactive. Okay. So the activation functions become inactive. Okay. It rises due to with certain neurons utilizing ReLU become inactive or dead. Okay. Yeah, this is what about when the ReLU activation function is getting died. Okay. Yeah. So for there are several factors that contribute to the occurrence of dying ReLU. Okay. So ReLU activation functions can be also dead or become inactive when there is no proper weight initialization. Okay. So if you don't have any proper weight initialization, in that case also ReLU activation functions will be inactive. Okay. If the data is also unbalanced, so if the data is unbalanced, then also ReLU activation function fails. It will become inactive. Okay. Consequence of dying ReLU. Okay. So what are the problems? So what if this ReLU activation function get vanished or become inactive? Okay. These are the problems. Okay. So we will be left with gradient descent. Okay, as we have seen. So learning impediment. Okay, so learning impediment will be also there if the ReLU activation functions inactive. Even though we apply, it becomes inactive during our process, means we may face these problems. Okay, they will not contribute to the model. Okay, neurons will not contribute to much information. Okay, That is what learning impedant means. Okay. Next, mitigation strategies. So what are the mitigation strategies that can be used in order to avoid? Okay, so there will be a proper weight initialization. So there are different weight initializations techniques also that we can see in further sessions. Okay, in order to make the ReLU activation function active. Okay, yeah. So on the whole, we can conclude there is a vanishing gradient problem that is occurring due to various activation functions, and that problem is overcome by various ReLU ReLU problems. Okay, ReLU activation functions. Okay, so there are different ReLU activation functions. There are subcategories under it, so which will help us to overcome this vanishing gradient problem. Okay, so that's it for this session. I hope you learned how to make the neuron active and how to get it pass the information to the next neuron. Okay, so thank you all. So thank you for giving this opportunity. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.